So at least personally, for my own notes and things like that, I refer to this section as vectors in 3 space. What we're doing is we're extending the usual X and Y into X, Y, and Z. So everything else extends as well. Instead of I being the vector 1, 0, it's now 1, 0, 0. And vector J, likewise, J is 0, 1, 0, and K is 0, 0, 1. So you've got 3 dimensions now. Well, now, as far as points in space are concerned, we can't call them ordered pairs anymore. Sometimes people call them ordered triples. I like the word 3-tuple, but I don't know, it's just kind of a cool way to say things. But right now we're going to start out with this point here, and this point actually kind of defines one of the corners of a box. So let me see if I can't hint at some of the other corners of the box. And we're going to get a corner of the box that goes between this point here. And how come you're not showing up? Let me try you again. Here over to here. So that's going to put us at another point. Now, why did it disappear? Let me try this. There we go. And it's disappearing again. That's so annoying. Now, the coordinates follow what's called a right-hand system. The way you can think of it as a right-hand system is that if you were to grasp the z-axis, your thumb is going to point up towards the positive z-axis. Your index finger will point at you in the direction of the positive x-axis, and your middle finger will point in the direction of the positive y-axis. So x, y, and z. At the base of things down here, we've got the point 0, 0, 0. The goal is to try and figure out the other 6 points in this box. So for instance, if I drop straight down from this point 5, 2, 3 down to the xy plane, then I'm making the z coordinate equal to 0. So in other words, I'll still be at the coordinate of 5 and 2, but now the x coordinate is going to be 0. And I thought I would be able to just move this. What's going on with my, there. So that would be this point right here on the base of my drawing, 5, 2, and 0. How about if I move over to the left from here? If I move over to the left from here, then I'm moving towards 0 along the y-axis. If I move towards 0 along the y-axis, that's going to make the second coordinate equal to 0. So that would be this one, 5, 0, 0. A couple ways I can think of this point over here. Again, if you're moving towards the x-axis, excuse me, if you're moving towards y equals 0, that's going to make that middle coordinate 0. If I make that middle coordinate 0, that's going to be this point right here, 5, 0, 3. You could also think of it as starting out on the x-axis and moving up in the z direction. So you move up, you're changing the z-axis, so now you're at 5, 0, 3 as opposed to 5, 0, 0. Let's try a couple more here. So let me go over to this point right here. Which axis or which coordinate am I changing if I'm moving from point P over to this YZ plane?
The x.
Yeah, the x coordinate. And I'm changing the x coordinate to be 0. So what's the new coordinate going to be at that point? Can anyone figure that out? I'll give you a hint.
0, 2, 3.
0, 2, 3. Excellent. So 0, 2, 3 put that right there. Let's drop down now, down to the XY plane again. So I'm going to start at 0, 2, 3, and I'm going to make the Z coordinate 0. So if I make the Z coordinate 0, what does that give me?
0, 2, 0.
Excellent. 0, 2, 0. So that puts that one here. And finally, 0, 0, 3. Can anyone imagine where that one's going to go?
0, 0, 3.
That one's going to be right on the Z axis. Everything is 0 except the value for Z. So you can think of 0, 2, 3 as being this point. And if I move towards the Z axis, I'm changing the Y coordinate. And when I change that Y coordinate, I'm going to change it from 2 down to 0. So I'll get that one. And those are my remaining 6 points. So you can start out with 0, 0, 0, and this other given point, and come up with those 6 points. So that's just a little perspective on 3 space. Let me continue with one of the typical problems for vectors in 3 space. And that's something like this. Find the dot product and find the angle between V and W. So let me write these 2 vectors down. Let's see, we got V, I'm going to write it with angle brackets. So it's going to be 3, -4, and 1. And W is going to be 4, 1, and 2. And the first thing they asked us is to find the dot product. And that's kind of convenient because that's going to be part of the calculation of finding the angle between those 2. So the dot product V dot W is going to be 3 times 4 plus -4 times 1 plus 1 times 2. 12 minus 4 is 8 plus 2 is 10. So there's V dot W. Now how about the angle between those 2? Let me remind you of that formula. The cosine of the angle between those 2 is the dot product of the 2 divided by another product.
Length of V and length of W.
Beautiful. The product of the length of V and the length of W. Perfect. So the numerator we've already got. Let's find the length of V and the length of W down here. So that's going to be the square root of 3 squared plus -4 squared plus 1 squared. Be careful when you run across these negative numbers. A lot of times people will square this and get -16. If you get a negative value underneath your radical when you're calculating a length, there's something wrong. Because essentially that's an imaginary length, and we're not going to have anything like that in this course. So 9 plus 16 is 25, plus 1 is 26. The square root of 26. And then 4 squared plus 1 squared plus 2 squared is going to be square root of 21. Let's put all that together in here. It's going to be the dot product of V and W, which was 10, over the square root of 26 times the square root of 21. And I don't know if you want to take time to play with this a little bit or not. It's just probably convenient to put it as a square root of 546. Yeah, 546, not 564. Where's my Photoshop? There it is. All right.
Now, would it be wrong to make it cosine inverse of 10 over that?
No, that's exactly where we're going.
Oh.
So yeah, no, you're totally right. That's equal to that means theta is equal to the cosine inverse of 10 over the square root of 546. And that
Could
should
we
a
be in
negative one.
radians or degrees for this?
That's a great question. It doesn't say. I'm guessing that they're going to want it in radians.
Okay.
So let's do it in radians just for giggles.
Okay,
You know, to be honest, they probably would want it in degrees, but we can do both. So here we go. No, what's that? So right now I've got it in degrees. In fact, here, let me do it on this because it's a little easier to see what I'm doing. So this one's in radians. Second cosine 10 divided by the square root of 546. And then you got to hit a right arrow to exit the square root and then a parenthesis, bam. So that's in radians. So 1 radian is about 50-some, 54, 57 degrees. So, you know, 60 degrees, 70 degrees, something in there. But if you want it in degrees, just click the mode key, go down and change over to degrees. And boy, I don't feel like typing that whole expression in again. So you can just use the up arrow a couple times, highlight that expression, press enter to bring it down, and bam. There you go. There you got it in degrees or radians, whichever one you need, and then round appropriately. So the last problem in this section is something like this. And this one, I kind of left the answers here because we'll do maybe 1 or 2 of them. We're not going to do all of them. You're asked to find the direction cosines. Direction cosines are pretty cool. And it's something we can do in 3 dimensions. So let me help you find the direction cosines. It's just a way to, you know, it's kind of like a version of polar coordinates for 3 dimensions. It's just a different way to point in the direction of a vector. So you're going to have 3 direction cosines. Those are going to be the angles that your vector makes with the x, y, and z axes. So I'm trying to find my little box here again, my box in 3 space. So our vector is going to be something like this. It's going to be a point, or excuse me, it's going to be a line that starts out at the origin, 0, 0, 0, pointing towards some point. Now, one thing you could do to specify this point is specify its magnitude, which we'll call r, in keeping what we've done earlier. And then specify the angle that it makes with the x-axis, the angle that it makes with the y-axis, and the angle it makes with the z-axis. That's what you're doing. So in its way, similar to polar coordinates. So let's figure out what those are. Direction cosine. So our vector is 3, -2, and 6. I'm going to write that in kind of my angle brackets notation. 3, -2, and 6. So like that. If you want to find the direction cosines, we're first of all going to need to find r. R is just going to be the length of the vector. So r equals the length of vector v. 3 squared plus -2 squared plus 6 squared turns out to be the square root of 49, which is beautiful. That gives me a nice even 7. There's going to be 3 direction cosines. There's going to be alpha, and the cosine of alpha, when you're trying to find direction cosine, is just going to be this number divided by the length. So it's going to be your x coordinate divided by the length. I'm trying to think if I can do this in general here for you. If v is x, y, and z, and cosine of alpha would be x over the length of v. Cosine of beta is going to be y over the length of v. And cosine of gamma is going to be z over the length of v. These angles are your direction cosines. So if you're looking for things to put on a little cheat sheet or something like that, I would include this, just so you have your direction cosines handy. Now with this as a model, x over the length of v. Well, we know the length of v. That was 7. And your x coordinate was 3. With this, can someone tell me what alpha is going to equal, or how to find alpha?
Cosine inverse.
Cosine inverse.
Yeah, thank you both. Cosine inverse of 3 over 7. That's going to be like 60 some degrees, I think.
64.62.
64.62, which is perfect. All right. So just to mimic that calculation. So inverse cosine, 3 divided by 7. Yay, 64.62. Perfect. Let's figure out what beta is. So coming back over here, we got cosine beta. Cosine beta is going to be y over v. So what should I write here for cosine of beta?
-2/7.
Yeah. So -2, remember, this is your x, y, and z. So -2/7. So that means beta is going to be an obtuse angle. It's going to be some angle in the second quadrant. You should, I'll do it here. Cosine inverse of -2 divided by 7. I'm getting 106.6, like that. So 106.6. Beta equals cosine inverse of -2/7. And finally, can you guys figure out gamma? What would you do for gamma?
Cosine inverse of 6/7.
Yep. Z over the length. Length is 7. So 6/7.
31.
31?
Yeah, 31 degrees.
Awesome. Beautiful. And that's it. Now, there is something kind of cool about your direction cosines, and that is if you did cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma, that would equal 1. And you can prove it to yourself if you take this and square it, plus this and square it, plus this and square it. If you take all those squared, you should get 1. So it'd be 3/7 squared plus -2/7 squared plus 6/7 squared. If you total that up, you will get exactly 1. So nice. All right, that's it.